With TSMC's 2-nanometer process entering mass production in 2025, advanced processes enter the angstrom era. Backside power delivery is a key technology. Giants like TSMC, Intel, and Samsung are adopting it. What exactly is backside power delivery? How does it differ from front-side power delivery? How will it change the semiconductor industry? A chip contains hundreds of millions of transistors. Current drives the switching between transistors to compute signals like symbols, text, and images. Front-side power has over 10 layers of power lines to transmit current to the transistors. This is front-side power delivery. However, as manufacturing processes advance, transistor density continuously increases, and with 3D stacking and packaging, the number of layers keeps increasing. Resistance in power delivery also increases, leading to power loss. Compared to front-side power, backside power moves wiring to the wafer's backside to free up more space on the wafer's front side to place more transistors. The more transistors, the faster the chip's processing speed. According to Ohm's law, V equals I times R. Here, V is the voltage difference from energy loss as current passes a resistor, known as voltage drop or IR drop. I is current, R is resistance. With constant current, IR drop is tied to resistance. Therefore, backside power can reduce resistance to reduce power loss from voltage drop, making it more power efficient. As AI model training consumes a lot of power, the goal of chip design now is not just to improve performance and speed, but more importantly, to reduce power consumption to achieve power savings. This highlights the importance of backside power. Take TSMC's A16 chip as an example. With backside power delivery technology, chip density is increased by up to 1.1 times, and speed is increased by 8 to 10%. Additionally, power consumption is cut by 15 to 20%. Backside power's core structure includes TSVs and buried power rails. With backside power delivery, current flows from the backside power lines, passing through the TSVs. TSVs are cylindrical channels that penetrate the entire wafer, connecting the front and back sides of the wafer. These channels are filled with conductive materials like copper, polysilicon, or tungsten to enable current transmission. Current then flows through the buried power rails, distributed to each transistor, completing the power delivery. This structure improves current flow efficiency, but it brings technical challenges. First, engineers must redesign the power delivery network, laying out the wiring in a new way, increasing design complexity. Also, making TSVs and buried power rails is also needed, increasing manufacturing costs. The manufacturing of TSVs is particularly complex, since TSVs run through the entire wafer thickness. To increase the probability of successful drilling, the wafer must first be thinned. But thinned wafers can easily warp or even crack, causing a decrease in yield. Plus, the wafer dimensions are very small, so when creating TSVs, precise front-to-back wafer alignment is needed. Any minor error can cause performance loss or process failure. Despite many challenges, as it boosts chip performance and power efficiency, backside power still attracts major firms to invest. The backside power race now features TSMC, creating a three-way race with Samsung and Intel. According to its established plan, TSMC expects to launch its A16 chip with BPD in 2025, with mass production in 2026. Samsung's SF2Z chip with backside power delivery is scheduled for mass production in 2027. And Intel, vowing to regain its leadership, aims for mass production of its 18A chip in 2025, putting its progress ahead of TSMC. While the race's outcome is still unknown, it is certain that, pushed by accelerated R&D from the three giants, backside power may change the rules of chip making, bringing a new direction to the semiconductor field.